so there it is. Nothing much left to do. Just to review, or also I can look at your work on Cloud9 if you want me to look at some of your code and criticize it, help show you how to find bugs. What do you want to do today?
We never went over the midterm.
Huh?
We never went over the midterm.
We didn't go over the midterm? Oh, I didn't know that. Okay, let's go over the midterm. Let's see. All right. Let me pull that up. Okay, here we go. Count negatives. Implement the function count negatives, whose declaration appears in figure 1. The first argument of the function a is an array of integers, and the second argument, len, is the number of elements in the array. The function returns the number of negative numbers in A. All right, let's let me do it like this. So here's the midterm. So this would be 1. And this is the function. Call it the function signature. You don't need to copy that in the midterm. You can just omit that. So I'll just show you how I would answer this, okay, on my own midterm. So we have to know how many negative numbers are in A. So we'll need a for loop to control an index that goes from 0 to len, the length of A. There's an index, I, that goes from 0 to len. When I hits len, the body of the loop, the substatements of the loop, don't execute anymore, and the loop is finished. So for each I, we want to check to see if A of I is negative. Is that a negative number? If it is, then we'll increase some count that we're maintaining. And at the very end, we'll return that count. Oh, but that means we'll need to declare the count and initialize it to 0. As in C++, there's no automatic initialization in this situation. Other languages will initialize count to 0, but not this language. So that's number 1. Any questions on that one? What about number 2? You see, this is all I'm writing on the exam. I didn't copy this. If you want to copy this, you can. That helps you think, that's fine. And so this code here, when this code runs, what does it print? So when this code runs, what does it print? Well, there's two variables in there, n and k. So we can think of it as having two buckets. There's the n bucket and the k bucket. We have to keep track of what these two buckets contain as we execute the program. So we do it, there's an order. We do one thing after another. Everything doesn't happen all at once. We have to do one thing after another. The first thing we do is a statement in line 11. Here, n gets created. N is a bucket. It holds integers. It's of type integer, type int. N gets created, and it gets initialized to 5. So variable n now labels a memory location that contains a 5. Now, in the next line, you'll see we create a k, and then we assign to that k the result of the right-hand side of the assignment operator. So before we can do that assignment, we need to evaluate the right-hand side. We need to evaluate this expression. And once we evaluate that expression, we copy it into the memory labeled by k. We copy it into the k bucket. So something's going to get put into here. So what gets into k? Also, n, the variable n, the memory identified by n, will be modified due to this increment operation. This is a pre-increment operator right here. This one here is a post-increment operator because it follows the variable. This plus plus precedes the variable. So they have two different ways of running in the code. In the case where plus plus precedes the variable, then you want to increment that variable immediately before doing anything else. So let's go ahead and do that. Let's increment n. So it goes from 5 to 6. So after you increment n, then this expression is taken as evaluating to 6. It's taken as evaluating to the value it becomes after the increment. That's the opposite of this one. This expression is taken to be the value of n before the increment. This expression evaluates to the value of n before the increment operation is performed. This expression evaluates to n after the increment operation is performed. Does everyone get that? I'm going to repeat it a couple of times there. So this expression evaluates to 6. So now we have 6 times 2. That's the next expression to evaluate. 6 times 2 is 12. So what I have highlighted right there evaluates to 12. That's the right-hand side of an assignment. This assignment. So we copy 12 into the memory identified by k. So 12 gets placed into the k bucket. And we're finished line 12. What about line 13? So line 13, this notation, this just means to add the right-hand side into the k bucket. Maybe this is more familiar to you. This this notation. This is the same thing. That might be easier for you to think about. These are equivalent, those two statements. So we have to evaluate what's on the right-hand side and add it into the K bucket, whatever values in the K bucket, whatever values in the memory identified by K. So what's the value of this expression? Who can say, if you've been listening? Huh? 6. The value of that expression is 6. And then you add that into K. So K becomes 18. But we also need to increment N. We do that after we evaluate this expression, then we can perform that operation. So N becomes 7. So I assigned to K first, and then I went back and incremented N. So line 13 is finished. And what about line 14? We have two operations. We have addition and output. We need to do the addition first. It has higher precedence. We evaluate this expression, N plus K, and the result becomes the right-hand side of this output operation. The C out is the left-hand side. So N plus K evaluates to 7 plus 18, which is 25. So we print 25. 25 becomes the right-hand side of this output operation. So the answer is 25. Question? What about this one? Count occurrences. Implement the function count occurrences whose declaration appears in figure 3. The first argument of the function A is a 100 by 200 two-dimensional array of int. And the second argument K is an integer. The function returns the number of times K appears in A. Oops. Don't need to do that. So how many times does K appear in A? Well, we're going to need something like this. At the core of this logic, we're going to compare A of RC, row column, or you could use I and J or whatever. If A of RC equals K, that means we found an occurrence of K at position RC, row R, column C. So it's the same as the other problem. If we find a K, then we're going to increment some count. Well, we don't have to call it count. We could call it, whatever, occurrences. We do it like that. So that's just a name of our choosing, just like the indices, the variables for the indices. So that means we need to have, all possible values. We need to look at all possible values for R and C. So we use two for loops for that. So the Let R range from 0 to 100. Let C range from 0 to 200. And then have our little piece of logic in there that uses R and C to check the value at position, row R, column C, to see if that value at that position is K. If it is, increment occurrences. And then once we exit these loops, we'll return occurrences because we're in a function. We also need to initialize occurrences. So it's pretty much the same as the first one, isn't it? It's just that we have a two-dimensional array instead of a single-dimensional array. For a single-dimensional array, we only need a single loop. We only need a single index. But for a two-dimensional array, we need two indices. So we need two loops, a nested loop. Any questions on that one? All right. What about 4? When the code in figure 4 runs, what does it print? So we have to analyze this code. When that code runs, what does it print? Well, there's only one variable here, look, I. So we only need to keep track of the memory labeled I. So in line 33, we create I, we create the memory and label it I. The memory is designed to represent an integer or an int. That's why we have the type here. So we declare I of type int. And then we initialize it to 66. So this I bucket, we put a 66 in there. After that's done, line 33 is finished. We've done that task. That instruction has been executed. Now the next instruction is lines 34, 35, and 36. The next statement that we execute is this while loop. You can think of that as one statement. It has a substatement in it. This is the substatement. The while loop repeats the substatement as long as the loop condition is true. So we look at the loop condition. If the loop condition evaluates to true, we execute the substatement. And then we check the loop condition again. If it's true, execute the substatement. We'll keep doing that until the time when we check the loop condition and it's false. And when the loop condition evaluates the false, it means that this while statement has finished executing. And we can go on to the next statement, which is the statement in line 37. So when we go to run this loop, what do we do first? Do we evaluate the loop condition first, or do we run the substatement first? We evaluate the loop condition first, so that's how we do it. It's the same as a for loop. Well, always, we don't just start with a do while loop. You always evaluate, you always run the substatements at least once. Because do while, and we didn't look at do while, but do while puts the condition at the end of the substatements. But this while loop, the condition is checked first, and then the substatements are done if the condition is true. So I is greater than 3, it's true, because I is currently 66. Now, when I want to check the loop condition, your I should not go to line 33. That's done, see? Your I should go to line 39. Line 39 represents the current state of the memory labeled I. Line 33 is not the memory labeled I. Line 33 is a statement that has run. So don't let the I go there. I see students do this a lot. They can't quite. You've got to bring into your thinking process that this line 33, that these statements that have already run have already completed, and you can't look at what they did in the past to help you evaluate that loop condition, because you need to keep track of the state of I separately from the instruction that initializes I here. So let's evaluate the loop condition. I see from line 39 that I is 66. 66 is greater than 3. The loop condition is true. So let's evaluate the substatement. The substatement is an assignment to I. We copy something into I. So there's 66 in I right now. So we're going to overwrite 66 with a new value. We get that value from the right-hand side of the assignment operation. The right-hand side is an expression, I divided by 2. And that's integer division, by the way, not floating point division. Because I is an integer and 2 is an integer. If we had a 2.0, that would be floating point division. And we would get a different result. Actually, we wouldn't get a different result in this case, but in other cases we would get a different result, but not in this one. Because we're still packing the result inside an integer, so we're going to drop the fractional component that results from that division anyway. So it doesn't matter if the division is defined as floating point or integer, because the result is packed into an integer. We have to drop the fractional component anyway. So what is I divided by 2? Once again, don't let your I go up to line 33. That's not where to look. Your I should go down to line 39. That's where we're keeping track of I. So get into that discipline, that habit. Or if you don't write it down, you have a mental note of what I is. Don't let line 33 suffice as your mental note. If you need a written mental note of what I is, then write it down separately from line 33. Create another place where you maybe have a box labeled I, and you're managing the contents of that box. You can do it mentally. But I see students so often, they go, oh, what's I? And then they go back and look in line 33. That's not going to work. So I is 66. 66 divided by 2 is 33. This expression evaluates to 33. 33 is then copied into the I bucket. It's written into the memory labeled I. It overwrites what's currently there. So what's currently there is 66. We're going to overwrite it, and it becomes 33. I is now 33. Now we've completed the substatement in line 35, so now let's evaluate the loop condition again. Is I greater than 3? I look down at line 39, and that's where I keep a record of what I is. I is 33. Is I greater than 3? True, it's true. So we execute the substatement. Divide I by 2 and store it into I. What's I divided by 2? 16. Because it's integer division. It's not 16 and a half. So that's 16. Let me do it like this. We started at 66. Then we got to 33. Then we got to 16. And so now we check the loop condition. Is 16 greater than 3? Yes, it is. So the loop condition is true. We execute the substatement. So we take I divided by 2, get 8, copy the 8 into I. So I now no longer represents 16. I now represents 8. And we keep doing that. Obviously, we can kind of skip a few micro steps here. When I becomes 4, 4 is greater than 3. So the loop condition is true. So then we divide 4 by 2, we get 2 and assign it into I. So now I becomes 2. Check the loop condition. Is 2 greater than 3? No. No, 2 is not greater than 3. The loop condition is false. The while loop has completed. And we go to the next statement, which is the statement in line 37. So whatever I represents is written into the output stream, appears on the display. So this thing will print a 2. Any questions on that one? All right, what about 5? Minimum. Provide an implementation of the minimum function whose declaration is shown in figure 5. The first argument of the function is an array of int, and the second argument is the number of ints that are in the array. The function returns the smallest number that is in the array. Now let's do this one. So we're going to find the smallest number. So we have to look at every value in A. So we're going to sort of keep track of what we think is the smallest number. I'll use the variable smallest. I'll call it smallest. And I'll set it equal to A of 0. I'll take the first one. I'm assuming that the array A has at least one element. So I'm just going to assume that n is always at least 1. The number of elements in A is at least 1. Yeah.
Could you do the same thing if you were trying to find the maximum?
Yeah. Int maximum is the same thing. Then this would be largest equals A0.
So you do that. If you do just a blank space,
Huh?
you put A when you don't declare anything.
Well, if you were going to do, let's suppose you're going to do maximum. Same thing. Oh no, let's not call it smallest, right? Let's call it largest. Same thing. Because we don't know what's in A. The maximum, it could, we don't want to start at 0. Because what if A has all negative numbers in it? Then we're going to end up with a 0 at the end, which is bigger than the biggest number in A. As likewise, for smallest, we don't want to start with 0 because maybe there's only positive numbers in A, which means that when we end up with 0, we're going to have a number that's smaller than all the numbers in A, not the smallest one in A. So it's the same process. We got to look at all the numbers in A. So we're going to need a loop, right? We got to have a loop for that. And then we'll have that condition if A of I, if AI is less than our current smallest, then we have found a new candidate at I to be the smallest element in A. Does that make sense? So we have to look at every element in A. So we need to use this variable index I and have it start at 0 and then go to 1 and go to 2 and so on. And for each of those values, we're going to successively compare those values to our record, our changing guesstimate of what the smallest element is. And by the time we reach the end of the array, then the variable smallest will in fact represent the smallest value in A if we use this process. Just to flush it out. What about largest? And we get a range through all the elements anyway, right? So if A of I is bigger than, if we find a new largest, then then we want to adjust what we think is the largest. So this variable largest really represents the largest we've seen so far. And when you get to the very last element, the largest we've seen so far, well, we've seen everything, so that's got to be the largest. And by the way, we need to return. So this is a function. Any questions on these? All right, what about 6? Write code that prompts the user. Now, it doesn't say implement a function, so we don't need to return. Just write a block of code that does something. Write code that prompts the user to enter a number between 3 and 12 inclusive. That means the user can enter a 12 or a 3. That's good. If the user enters a number inside 312, the program displays good number. Otherwise, the program displays bad number. So 3 and 12. So let me go back there. I kind of forgot what I was doing. Prompt the user. We have to prompt the user to enter a number between 3 and 12. Prompt the user. It's just a snippet of code, we'll call it. Prompt the user. Enter a number in 312. Maybe I'll put a colon and a space there. We don't want to go to the next line. We want to stay on that line. And we'll need to read that number in. I'll call it n. So you have to create the n, and then in line 63, and then in line 64, we use the input operation on the input stream to pull a value from the input stream and copy it into n. And then now n has to be, we're going to do something here. If this, then we're going to say, good number. Otherwise, we'll say bad number. So what is the condition here? It has to be bigger than 3 or equal to it, and less than or equal to 12. So n has to be larger than or equal to 3, and n has to be less than or equal to 12. Then it's a good number. You could do it. There's different ways of solving the problem. I'll show you. Here's an alternative way to do the problem. If n is less than 3, or n is greater than 12, then we're going to print bad number. Else we're going to print good number. You can do it like that. Now here's another one. It says you can do it in many different ways. If n is less than 3, although I don't recommend this way to do it, you can do it like this. If n is less than 3, print bad number. Else, if n is greater than 12, print bad number. Else, print good number. So that's an if, else, else. So there's two cases where we print bad number. First, we check if n is less than 3, we know it's not in that interval. Let's print bad number. Then, if that's false, if n is not less than 3, let's see if n is greater than 12. If it's greater than 12, then it's not in that interval. Let's print bad number. Else, well, we checked if it's too little, we checked if it's too big. Must be a good number. But here you see we're duplicating code. This line here is code duplication. This operation here, this statement, is the same as that statement. So this is a more efficient way to do it. We just check, or not more efficient, it's not the right word. It avoids code duplication. But you know, you don't have to be rigid about it. If code duplication is sometimes all right, if it improves clarity.
Right, is it just the second example, isn't that tautology? Well, not tautology, but
Which one? What in the line number?
72 wouldn't always be true.
32?
72.
72?
Because you could say,
No, it's an or there.
yeah,
So what about 5? Is it true that 5 is less than 3 or 5 is greater than 12? You know, 5.
yeah.
You want, 5 is not, so that's false. So 5 is a good number. Now, if we had an and there, see, that's an or. This is an and. Right? And this is an or. So it's not always true. If we had n is less than 3 and n is greater than 12, well, that is always false. Always. Because there is no n that is both less than 3 and greater than 12. By the way, normally in code you'll see that. That's the typical. And for and, you'll see this. Even though they're allowing the word and or now, this is what you'll see in most code. Also in other languages, all the languages that I can think of use these symbols. Not all of them. But that's an or, and this is an and. Any other questions? All right, let's go to the next one. 7. Is prime. Implement a function that takes a single integer argument k. The function returns true when k is prime and false otherwise. So we're going to do something. The algorithm that we've been using here is to try to divide k by all the numbers from 2 up to and including k minus 1. So we use a loop. We start the loop at 2. We go up to k, but we don't use k. We just use k minus 1. We need to increment that variable I. Now, we check to see if k is evenly divisible by I. In other words, if k mod I is 0, so mod is a remainder operator. If the remainder resulting from dividing k by I, if that remainder is 0, then k cannot be prime. So we just return false on the spot. No reason to finish with the loop. We return from the function. The function returns a Boolean value. So we need to return true or false. We found a divisor I that doesn't produce a remainder. So we return false. If we complete the loop and we never find such a divisor, then we know that k doesn't have a divisor. It must be prime. So we return true that k is prime. Now, this is good enough for this class, but you could do a little better. This is kind of obvious one here. Not too obvious, but you don't have to go past the square root of k. That runs a little faster. Well, a lot faster. But you don't need to remember that or do that. But if you like, that's great. How about this? If you put that in square root k in your exam, I'll give you 5 points extra credit. I know. Shouldn't make jokes about grades, but you know, if you can remember that, there you go. All right. What about 8? Write code that prints 100 random integers that fall between 500 and 2,000. So print 100 random integers that fall between 500 and 2,000. So what students do with this problem is they get the numbers confused. They end up printing 2,000 random integers between 100 and 500 or something like that. So you got to just sort of keep this straight, right? So you're going to go back and check your work on this one. 100 random, I'm just going to forget about, I know I've got to print 100 things, okay, 100 things. I got to print 100 things. I got to do something 100 times. So just start with a loop that runs 100 times. There it is. That's a loop that runs 100 times. So we do something. So we're going to do something 100 times. So right away, I've sort of factored out this part here, this 100. Now I can forget about 100. I got that done. What are we going to do? Print random integers that fall between, we're going to print a random integer in that loop that falls between 500 and 2000. So we're going to print a random integer. I'll call it n. All right? And n will be the random integer. 500, 2000. Just do it like that, just a little pseudocode there. So how do we get a random integer? Well, our trick was, we do need to declare n, by the way. Our trick here is to, now this may be a little confusing for people. We need to, n needs to exist, so we can declare it like that, and then we can assign a value to. If you want to do it like that in 2 steps, that's what really happens. N gets created, and then we copy a value into it. You think of it like that anyway. So the range, in 500 to 2000, that range is 1500. So we got to have 500 and add a random number in 0, 1500. So that's how we do it. So a random, but in 0, 1500, that's rand mod 1500. So this expression, we take a random integer, which could be very big, we divide by 1500. And then it gives us an integer that's between 0 and 1,499, inclusive. We'll never get 1500 as a result of this expression because, you know, you can't get 1500 as a remainder when you divide by 1500. That's not possible. The biggest number you're going to get is 1499. So there's our expression. We can leave that in there as a comment if we like. You can do that. I like to do this all in one line. I don't like to, you know, initialize or declare n separately, but you can do it that way. The way I just showed you is all right. So is this exactly right? Do we, because this is inclusive, does this expression really sometimes produce a 500? And does it sometimes produce 2000? Or are we off by 1? Remember the off by 1 problem? I don't know if I mentioned that. Off by 1 is a typical problem in computer science. You got to check always if you're off by 1. So let's see. What's the smallest value that this will produce right there? 0. And therefore, what's the smallest value that that will produce? 0. So the smallest value that this produces, 500. So we do get a 500. So it's inclusive. We can produce a 500 with that code. Now let's ask the question, is it possible to produce a 2000 and nothing higher? What's the largest value that this can produce? Well, we don't know. Big, right? Really big. All right, so what's the largest value that this can produce? Huh? Yeah, $14.99. Biggest number that we can produce there is $14.99. What's $14.99 plus 500? That's $19.99. Sounds like something that's for sale at the store. So we're never going to hit 2,000. We're only going to hit $19.99. So we got to bump this up. It has to be 1501. Now we're going to hit 2,000. Because now, if we go back through the reasoning, just to double check, see, we were off by 1. We're off by 1. That's the off by 1 mystery that always crops up all the time. Or not mystery, but the off by 1 problem, they call it. So the largest value that this expression evaluates to is 1,500. And so the largest value that this evaluates to is 2,000, which is what we need. The largest needs to be 2,000. So there is the answer.
But then does it shift it to 501?
Huh?
Is it shifted to 501 or is it still at 500?
No.
Is it 0 to 1,500?
No. This is because the biggest is it's 1501 here, and 500 is just 500. We leave that because if we made this 501, then this is going to be the lowest will be a 0, and then we're not going to hit 500 anymore. And also, this is we're going to go past. We're going to go to 2001 now. We're going to go 501 to 2001. So, see, that question that you just asked is excellent. That's what you're supposed to do. You know, you feel it. You have a hunch that you should not set that to 501. You know that that's wrong. You have a feeling, a gut feeling. But don't go with a gut feeling by itself. You got to say, well, I could still be off by 1. I still might have I got to check my reasoning. I'll take the position, which I feel is wrong, just to analyze it, to increase my confidence. So that is the right mental discipline that you want to develop. Yeah.
If it wasn't inclusive at 2,000, would you just leave it at 1,500?
If it was not inclusive at 2,000, if it was, if I put a little parenthesis there, that's the math notation. That means exclude 2,000, but include 1999. Yeah, then it's 1 less, and then we go to 1,500. That's right. Yeah, and that. Be prepared for those kind of things on the finals. I might actually ask that. Okay. I better put that back. That's great. Okay. Nine. Oh, these here. I wanted to say that these questions about the Unix commands are very important for the computer science, computer engineering, computer system majors here. Okay. For the other majors, they might be important at some point in your life. I don't know. But for the computer majors, you got to know this stuff because you'll need it in your other courses. And of course, when you graduate, you'll be expected to know this kind of stuff as well. So I'm just saying that it's important, that's all. I didn't used to have these questions on the exams, but the professors teaching the later classes were complaining that the students didn't know how to do this. So I started putting these questions on the exams to get you ready for that later on. So suppose your home directory contains a folder named temp. Well, that would be like, well, we don't have a home directory here, do we? But we can make it look like that. The home directory, if I do CD enter, I go to the home directory and see the tilde here? That symbol represents home directory. See, practice the Unix commands. pwd, cd, copy, cp, mv for move, rm for remove, mkdir, make directory, rmdir, remove directory. And then you have these special symbols, dot, 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 and tilde. Tilde means home directory, dot, dot means your parent directory, and dot means current directory or folder. The word directory means the same thing as folder. The original word was directory, and then at some point in the industry or the community, they started to use the word folder to be more user-friendly, that people could visualize a folder, something that contains other things. So then the word folder got caught on. But I remember the old days, nobody used the word folder. It was not used in this context. It was always just a directory. You have a question there?
How do I use the symbols, the dot and the dot?
All right, I'll show you that. For one thing, the question is, how do we use the symbols dot, 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 and tilde? Well, for one thing, you can recognize that that tilde is being displayed there in the prompt. That means you're in your home directory. If I use ls, I can see that I have 3 subdirectories in my home directory. And I can change my directory to SAM. Now look at the prompt, and now it shows the path from my home folder to the SAM folder. That's called a path. The path uses slashes to separate components. The first component is the tilde, which means the home directory. The second component is SAM, which is the current folder. If I print working directory, it doesn't print tilde SAM, but it prints, /home/ubuntu/SAM. That's because tilde equals /home/ubuntu. See, if I do ls tilde, I get those 3 folders. If I do ls/home/ubuntu, I get the same 3 folders. It's the same thing. Tilde and /home/ubuntu are the same thing. They represent the same thing, the same directory. Now, I'm inside SAM. If I go pwd, print working directory, I see that I'm here in the file system. And by the way, in this recommendation I gave to you at the very beginning, there's a link to this tutorial on the command line. So if you haven't done that yet, then you should do that. Or if you haven't fully mastered the commands, go back and do it again. So that's a free tutorial online. It's very nice. So let's suppose we want to go to the home folder. We can get there in many different ways. The home folder is the parent folder. We're in SAM, but SAM is in the home folder. So I can go to the parent by going change directory to the parent. Here's the dot dot. I'm trying to show you the dot dot here.
Could you explain how the parent folder is the home folder? What does the parent folder mean?
The parent folder is the folder that contains the folder you're in.
Oh.
We're in the SAM folder. The SAM folder is in the Ubuntu folder. The Ubuntu folder is the parent folder of the SAM folder. You can see that in the path. Ubuntu/SAM. The SAM is to the right of the slash. Ubuntu is to the left of the slash. That means SAM is inside of Ubuntu. Likewise, Ubuntu is inside of home. And home is inside of the root. The root is where it stops. It's called the root folder. We can look at what's in the root folder. I can do ls/. That's the root folder. It goes all the way to the top. That's the root folder. Now this root folder has an Ubuntu subfolder in it. I'm sorry, it has a home folder in it. It says home, it's not your home folder, it's just the word home. It contains home folders. There's only one home folder in it called Ubuntu, home directory. And inside home, there is, the Ubuntu. Inside there is SAM. So this, see, I'm using different paths as an argument to LS. So LS produces a listing of the contents of a folder. Now, if I omit the argument to LS, it gives me the contents of the current folder. So it's the same as doing ls dot. Dot means current folder. So those produce the same thing. Yeah.
So when you're listing the contents of the directory, if you're listing the contents of any directory, if you're listing the name, you precede it with a forward slash, but if you're using the symbols, you don't precede it by a forward slash.
Not exactly. That you can't just follow that rule. Yeah, don't memorize that rule. I don't recommend that. So if you want to look at, let me show you. I go to here, okay? CD, watch me. I'm going to look at the contents of the SAM folder. I just do it like that. So that's a counterexample that goes against the rule that you just stated. So this is a relative path, SAM. I'm not preceding it with a special character, tilde, dot, or dot, dot. And I don't precede it with a slash either, right? So that shows a counterexample to that rule you just suggested. So there's two kinds of paths. There are absolute paths, and there are relative paths. A relative path, its meaning depends on your current directory. But an absolute path is a path that has the same meaning no matter where you are in the file system. I'll give you an example. If I do ls/home /Ubuntu, that's an absolute path. See, it produces this, right? If I'm inside SAM and I use the same absolute path, I get the same result. So absolute means it's the same wherever you are. But if I do ls dot dot, I'm saying show me the contents of the parent. Now dot dot by itself is a relative path. Its meaning depends on where you are in the file system. This /home/Ubuntu does not depend. It's a path that does not depend on where you are in the file system. So we call it an absolute path. So see, ls right now gives us that. But if we go up a folder and then we do ls dot dot, we get a different result. So ls dot dot gives us a result that depends on where we are. So dot dot is a relative path. So let's go back into SAM. Is that a relative path or an absolute path? Huh?
Absolutely. I would say relative. The sound could be in different places.
Yeah, it's a relative path. This path assumes that there's a folder called SAM that's a subfolder of my current folder. Is that an absolute or relative path?
Still relative.
That's right, it's a relative path. It's relative to the current folder. Is this an absolute or a relative path?
Absolutely.
Absolute, good, very good. This has the same meaning, doesn't matter where you are. Of course, this doesn't exist, I think. Oh, no, it does exist, doesn't it? It does exist, sorry. That's good, very nice. PWD, that's print working directory. Where's our working directory? Working directory also means your current directory, so same thing. These are very old words that were created a long time ago, you know, when I was younger than you. What else do we want to do here? Oh, we're going to do this. Suppose your home directory contains a folder named temp. Let's do that. Let's create in our home directory, I'm going to go to the home directory, cd tilde. By the way, it's the same as just cd by itself. It's the same thing. It's going to put us in the home directory. Or cd/home Ubuntu. They all put us in those three things put us in the home directory using absolute paths. So let's make a directory called temp, mkdir temp. I used a relative path to make the directory temp. Now look, in addition to lib, sam, and workspace, we now have a fourth directory named temp. Show the Unix command to list the contents of that folder. Make no assumptions about the location of your current directory. So that means you need to use an absolute path. A relative path won't work because the relative path depends on your current directory. You know what? We're running out of time. I am like going over this exam so slowly. I hope that it's valuable to you for me to go this slow. Maybe we have another meeting, right, on Thursday. So we can continue on Thursday. We'll come back and finish from number 9 and go forward from there.